Hello everyone and welcome to this training session on actuarial common entrance test ASET. As a part of this session, I would be taking up the one of the chapters in mathematics. As you are all aware that mathematics or numerical methods, whatever we call, there are 8 chapters involved in that particular subject and 12 in statistics per our ASET entrance exam. And as a part of that mathematics, I would like to cover the chapter which is the first one as a part of the curriculum, which is on notation. So, as a part of this chapter called notation, what is that we need to understand from an exam standpoint? So, let's get started with topic by topic under this particular chapter. The first The first thing as a part of this curriculum that we need to be comfortable with is understanding the different types of numbers. So, whenever we see any kind of a number, what category it falls into, so what are the various types of numbers that are available, this is something we need to be pretty much comfortable with. So, the way I would like to start off with is the whole gamut of numbers. The whole gamut of numbers will be broken down into two aspects. One, I call them as real numbers, generally denoted by a symbol called R, or I have complex or imaginary numbers. We call them either complex or imaginary. They are generally denoted by C. This is one category of numbers. What are these two? Any number which exists in the real world, we call all of them as real numbers. It could be 2, 3, 4, 4.2, 7.5, 22 by 7, whatever. Any number that exists in the real world and can be represented on a number line. Let's say I put a number line like this, starting from 0, 1, 2, so on. I should be able to mark that particular number on this number line. Then I call those kind of numbers as real numbers. And if I cannot mark them as real, then they become complex or imaginary. For example, I say square root of minus 2. We know that the square roots are defined only for positive numbers. Then how do I find out the square root of minus 2? It does not exist in the real world. So for any of those numbers that cannot exist in the real world, we categorize them as complex or imaginary numbers. Right? So most of our dealing will be with the real numbers itself. The world of complex numbers is completely different and it has to be studied differently, and we are not much bothered as far as our ASET is concerned. We are not much bothered about the complex or imaginary numbers. Our focus is primarily on the real numbers itself. Right? Then this real numbers, again I can categorize them into two broad groups called as the rational numbers or irrational numbers. Generally the rational numbers are denoted by Q, whereas irrational numbers, yeah, sometimes people use the notation I, but again we anything which is not rational, we call it as irrational. Then how do we define this something called rational? Any number which can be expressed in this form of P by Q. So if I take the number 3, I can very well write it as 3 by 1. Or probably if I take 2.2, I can write it as 22 by 10. Any number which can be expressed in the form of P by Q, where P and Q, both of them, they belong to the world of integers. What is this world of integers? They should be numbers. They cannot be decimals, they cannot be anything else. They should be proper numbers, either positive or negative numbers. No decimals, no fraction, no decimals. Both the numerator and denominator should be proper numbers, either with a positive sign or with a negative sign. So anything which can be expressed in the form of P by Q, where P and Q belong to the world of integers, and Q is not equal to 0, denominator is not equal to 0, we call such kind of numbers, as rational numbers, where Q should not be equal to 0. We call such kind of numbers as rational numbers. Any number which is not rational, we treat it as an irrational number. So mostly all normal numbers, fractions, they all, or even decimals, they all go as rational numbers. But something which does not have any ending, let's say a square root of 2. So the actual value is 1.414 something 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 something. So it does not end anywhere. Any such kind of values which don't have a proper ending, or for that matter pi, which is generally written as 22 by 7. If I write it as 22 by 7, then it is rational because these two are same. But if I try to find out the value for it, 3.142, it won't end. It will never end. So these kind of numbers where there is no ending in the decimal form, we call them as irrational numbers. But if I can write it in the form of P by Q like this, then it goes under the category of rational. So for all practical purposes, pi, which means 22 by 7. So we need to understand something like this also. Pi means actual value is 3.142 so on, which means it's an irrational number, but it is approximated. Approximate is always written with this kind of a sign, equal to, with some kind of a tilde on the top of that. It is approximated to a value of 22 by 7, but it's not exact. So the exact value is this, which will never end. So that's the reason we call pi as an irrational number itself. So rational number is this, and the rational numbers can again get divided into integers and fractions. Integers are proper numbers, -3, -4, +2, 0. Those are the numbers which are called integers, and anything which is not an integer is called as a fraction. Integers are denoted by Z or Z. Then the integers, again we bring various categories of integers, which is natural numbers, which are counting numbers. When I say natural numbers, these are the numbers which are typically used for counting purpose, 1, 2, 3, so on. So they start from 1, 0 is not included under the world of natural numbers. So 1 to infinite, all the counting numbers which is denoted by n, so which is otherwise called as positive integers only, because integers can be negative, positive, as well as zero. Positive integers, otherwise denoted by this kind of a sign, z plus. Z plus is positive integers, because Z is all integers, plus means positive integers. So we need to be comfortable with this kind of a notation also. So Z plus is natural numbers. Then we also have a world of whole numbers, which is nothing but the group of natural numbers plus a zero also is included. So starts from 0, 1, 2, 3, so on up to infinite. So that is called as the world of whole numbers, which can also be written as the total set of integers minus the total set of negative integers. Because negative integers are minus 1, minus 2, minus 3, so on. So whole numbers contain the remaining group 0, 1, 2, 3. So we need to be comfortable with all these kind of notations. So even if someone places a plus on the top of any of these alphabets, so because we saw R is a world of real numbers, then Q is a world of rational numbers, Z is a world of integers, and N is a world of natural. In N, you don't find negative and positive, because N is always a positive. Whereas for all these things, they can put either plus or minus on the top of them to say that this is a set which contains only the positive real numbers or positive rational numbers and so on. So this is one aspect you need to be comfortable with, because there could be some questions which would be surrounding this particular concept. I hope everyone is comfortable with this aspect of the basic understanding of different forms of numbers. Then the next concept that you need to be comfortable with is some kind of symbols relating to notations. Sometimes we see some symbols like something like this, which says for all. For example, if I say for all x, for all x, x which are real, for all x is real, x square is real. So if x is real, then I say x square also is real. So that is the place where we use for all, or probably we'll say for all x is real, x square is positive real. Something like that. Because squared cannot be negative, I can very well try to put out some relationships like this. So whenever we see this kind of a notation, we say that it is for all kind of a notation. Or if I see this kind of a notation, an inverse E, this is called as at least one. Or there exists at least one. It's not for all. There exists at least one. And similarly, if we use a notation with a cross on it, there does not exist at least one. Right? These are some of the symbols and notations you have to be comfortable with. And a couple of other notations that you have to be comfortable with is implies. A implies B. Otherwise, it's also written as if A then B. It means if A is true, then B is also true. Then we say the word A implies B, which means once I know two, if there are two statements, let's say A and B. For example, A is a statement which says A is number is even, and on the other side I have a statement which says B, which says the number is divisible by 4. Then if I have to look at this, if a number is even, is it divisible by 4? If it is divisible by 4, then I say A implies B. Need not be the case. If the number is 2, 2 is not divisible by 4. So I cannot make a statement saying if a number is even, it is divisible by 4, which means A is not implying B. But look at the other relation, B implies A. If the number is divisible by 4, it is definitely even. It cannot be an odd number at all. So B implies A is coming from this statement, but not A implies B. Right? So like that, if both A implies B as well as B implies A, if both of them are coming out, then we will write it as A implies as well as implied by B, which means both sides we put the arrow marks, which is also called as implies and implied by kind of a relation. So it also works out to if and only if. So if A then B, if B then A. So if A, if and only if A then B. Right? That is what we call as implies and implied by kind of a relation. So at least these are some of the most common symbols we have to be comfortable with as far as this exam is concerned. Right? Then we move on to our next area here, which is understanding the basics of the set notation. Set is nothing but group of values or collection of values. So I may very well say a set A contains numbers 1, 2, 3, so on up to 10. Or a set of natural numbers, or a set of natural numbers lying between 20 and 40. So these are all sets. Set is nothing but a group or collection of some values. And a few things there. Set is denoted by this kind of braces, right? The elements of the set are given by comma separated, or sometimes some kind of notation is also given. The same thing is written like this. X, this is a symbol called belongs to. X belongs to natural numbers and X is less than or equal to 10. So it could, the same information 1, 2, 3, 4 up to 10 can be written either in this form or in this form. This form is called as the set builder form. So we are trying to build a set from this particular equation kind of stuff. So there could be a definite question on these things. He'll give a set builder form like this, and based on this he will ask you to create a set in this kind of a notation. So we need to, so here we are using the types of numbers to which that particular set belongs to, and at the same time the range of values that particular set can take. So taking these two into consideration, I should be able to identify the various elements of the set. And if the set does not contain any value, if the set does not contain any value, we call that set as a null set or even an empty set. So if the set does not contain any values, we can very well categorize it as a null set or an empty set, and sometimes denoted by a symbol called phi, or it is also denoted by just a simple braces without any values inside it. That is what we categorize as the null set. Then a few more things you have to be comfortable using inside in the set theory is, if I combine two sets, combine two or more sets, we can do using some notations like union or intersection or complement. Union is I'm combining two or more sets. So it is more like if the value is present in at least one, it's also written as A or B, or otherwise it is written as A union B, which means at least if it is present in A or in B, in any one of them, then it would be present in the union also. So if I take a set like this, if I take A is a set containing 1, 2, 3, 4, B is a set containing 2, 4, 6, 8, then if I have to denote A union B, all the values which are present both as a part of A as well as B are taken under the A union B kind of a relation. Or whereas if I go with intersection, it's more to do with the commonality between A and B. That is why it is also called as A and B kind of a relation, represented primarily by A intersection B, represented primarily by A intersection B. And going back to our example, here it takes only the common elements which are present both in A as well as B. 2 and 4 are the values that are present both in A as well as in B. That's one thing. And then whenever we talk about complement, whenever we talk about complement, we write either as a hash or sometimes we write it as a bar. It means from the total universe, let's say here we say the total universe is the numbers from the total universe, we generally represent it with something called a mu. Let's say it is from 1 to up to 8. then A complement is something which is there in the universe, but not in A, which means the elements 5, 6, 7, 8. These are there as a part of the universe, but they are not present in A, so that is what we call as A complement. Similarly, if someone wants B complement in the same thing, then it becomes 1, 3, 5, 7, because those are the numbers that are present in the universe, but they are not present in B. So this is one more notation you have to be comfortable with, and if we, and what I really feel is these kind of questions can make it to the exam to make things slightly tricky for you. There could be a couple of questions involving the union, the intersection, and the complement, and probably there could be some question which says, okay, given some set A, given some set B, some set C, find A intersection, B complement, union C. Some kind of calculation. All you have to do is break each of them separately. Find out first the B complement, because you will be having B but you will not have B complement. So create a new set called B complement, which is present in the universe but is not present in B. Create a B complement, and then do the intersection, which means something which are common both to A as well as to B complement. So that is your new set, right? And whatever the new value that comes out, then do a union with C, which means something that is present in that set as well as within C. So you have to do it as a step by step exercise itself to find out, to evaluate the answers in these kind of situations. So understanding of the set language, not just in the form of numbers but also in the set builder form, you need to be comfortable with, because a good number of questions could very well be involved based on the set builder form notation also. So making yourself comfortable in that space also will add a lot of value to your scoring in the exam. Then a few more things you need to be comfortable with is a few more notation is what I'll call. I'm sorry. A few more notations that you have to be comfortable with is some constants. As we have already discussed, pi as one of the constants whose value is 3.142 so on, and is approximated as 22 by 7. You need to have some kind of understanding of this. The most common constant which we use in our calculations world is E, which is also called as Euler's constant, whose value again is sometimes 2.718 and so on. We will use this E as a part of natural logarithms. When we discuss logarithms, we can discuss this E in quite a good nature. And applications wise, it has a lot of applications in the world of continuous compound rate calculations. So it's one of the very important constants in the world of mathematics. So you need to be very comfortable in terms of whenever you come across this word E, you will find it even in your calculators also. Whenever you come across this word called, this symbol called E, you need to be able to interpret its value. And we also talk about something called one single arrow like this, which is also called as tends to, which means approaches. When I say x tends to 0, it means x is not 0, but it is coming very close to 0. As x is coming closer and closer to 0, what is happening to 1 by x? It means, let's say, if x is 20, 1 by 20 means 0.05. So let's say it comes to 10, 1 by 10, which is zero point 0.1. X is 2, 1 by 2, zero point 0.5. X is 0.5, 1 by zero point 0.5, which is 2. As x is decreasing, 1 by x is actually increasing, and x is becoming very close to 0. What I see is 1 by 0, the 1 by x actually approaches infinite. Infinite is something, a very high positive value which cannot be defined also. That is what we call as infinite, and tends to is a relation which actually shows the pattern of the moment. If x is tending to 0, x is not actually 0, but it is coming closer and closer to 0, how is the particular value getting impacted? That is what is the usage of tends to in our typical notation. So even this particular aspect is something which you all need to be comfortable with as far as our exam goes. Then this chapter also focuses on you getting some kind of comfort level on some kind of Greek letters, very commonly used Greek letters. So some of the very commonly used ones I would like to touch upon here. We will use a Greek notation called sigma. This is called sigma, capital sigma, to actually denote summation. Very common ones only I am trying to identify. The capital sigma is used for denoting summation, whereas the small sigma is used a lot in statistics and called as standard deviation. Right? As we move along, we'll try to understand so many Greeks. Capital pi. This is capital pi, which is used to denote product of numbers, multiplication of numbers. Whereas small pi, it's a constant, mathematical constant 3.142, so on. This is one more number that is used very heavily. Then this is called as delta. Delta is used to denote a small change or difference. When I say delta x, we say that if there is a small change in the value of x, that is what we call it as a delta x. Delta is one more most commonly used symbol in the Greeks. Even the small delta is something like this. This also talks about, this also has some usages. Delta, which is used to denote the force of interest, again in the continuous rate of interest. And okay, a few more constants. This is called mu, which is generally used to denote the mean or the average of a data, again from a statistics standpoint. Then this is called rho. This is used to denote correlation between two data sets. We'll talk about these things in our stats, but yes, these are some of the constants. These are some of the Greek letters which are used heavily for various interpretation purposes. Of course, as and when we come across these kind of notation, we'll discuss them in detail, but some of the most commonly used ones. For a lot of statistics related stuff, we use something like alpha, beta, gamma, and then lambda, there are so many such things which are used as parameters in the world of statistics. Even theta. So all these things they are used as various parameters from various standpoint. But yeah, at least to these basic ones, if you are comfortable with, it helps you in solving a lot of numerical questions. All right, right. Then let's move on to the next aspect in this chapter, wherein sometimes if the number is pretty big like this, instead of solving numbers, doing all these, let's say into 120 something, if I have to do like this, instead of doing a calculation like this, if there are 6 digits already, if there are 6 digits in the number already, we can very well abbreviate it as 3m. 3m means 3 million. The last 6 digits can very well be approximated. Let's say it comes out 320000, because this is the last 2 digits. Probably I'll put a decimal point here and say 3.2m. It means 3.2 million. So probably I could do the calculation directly as 3 into 120 and directly say 360 million, instead of trying to apply this entire thing as a part of my formula. So that's one more thing you can be comfortable with. So anything related to million is represented by M, whereas anything that is related to thousand is related to K. If I say my salary is 25,000, or I can very well write it is 25K. It is also means 25,000. So K is a notation that is useful for denoting the thousands, whereas M is a notation that is useful for denoting the millions. And one more set of terminology you need to be comfortable with is percentage points versus basis points. So percentage points, let's say if the number is 8%, if some value is 8%, and when I say there is an increase by 2 percentage points, there is an increase by 2 percentage points, it means it has become 10%. A decrease by 2 percentage points, it means it is 6%. But if I say an increase by 2 basis points, from 8 there is an increase by 2 basis points, it means it has increased only by 8 it has become 8.02%, not 10%. 2 basis points is 2 by 100 percentage points. So 2 by 100 is 0.02 percentage points. 0.02 percentage points to 8 percentage points will make it 8.02 percentage. So you need to really differentiate between the words. Percentage point means literally there is a change in the percentage by that much. But when I say basis points, then I need to do by 100 to make it as a percentage point, and then add or subtract that number. That is what will give me the basis point to percentage point conversion. So if the question is given in percentage points, if I have to make it into basis points, then you multiply it by 100. But if you are given basis points and you have to convert them into percentage points, divide by 100. But to an existing percentage, you can add only the percentage points itself. So if the question is given in basis points, convert it into percentage points by dividing it by 100 and then add it to the existing percentage. That's one more aspect you have to be pretty much comfortable with. And then the next thing that is being covered in this chapter is when you have to prove something. We are talking about something called a necessary condition or a sufficient condition. If a particular condition is it necessary or sufficient or both necessary and sufficient. So this I'll take it with an example. X belongs to natural numbers and X ends with 5. This is a statement A. X belongs to natural numbers and it ends up with 5. There is a statement B which says X belongs to natural numbers and X is divisible by 5. Alright. Now I have to say, is A necessary for B or is A sufficient for B? Or is A both necessary as well as sufficient for B? So that is where our proving exercises will take their own dimensions. Now if I say A is necessary for B, then I will have to write, if I say A is a necessary condition for B, then I should be able to write it as B implies A. So it means if B then A. If X is divisible by 5, then X ends with 5. Is that the case? No, right? If X is divisible by 5, then it can either end up with a 5 or with a 0. Anything is possible. So if I say A is necessary for B, which means A is mandatory for B, which is also saying X has to end up with 5 if it has to be divisible by 5. That's not the case, right? So whenever I say something is necessary condition, A is a necessary condition for B, then it means it should follow the relation, it should satisfy the relation B implies A, or if B then A kind of a relation. Then only it becomes necessary. But if it has to be sufficient, then I can very well say A implies B should be true, which means if A then B. So here it's like if X ends up with 5, then it is divisible by 5. That is very much true. If a number is ending up with 5, I can very well say it is divisible by 5. There is no other wrong statement in it. But if it is divisible by 5, the reverse is not true. Right? You see it in both the cases. If X is ending up with 5, then I am sure that it is divisible by 5. Whereas if X is divisible by 5, then it need not end up with 5. It can end up with a 0 also, but still divisible by 5. So that is where we say we need to find out any condition or any statement which we are making about the proof. Is it a necessary condition or is it a sufficient condition, or in some cases both, it is necessary as well as sufficient also. In that case, this particular relation both should hold true. A implies B should hold true, B implies A should hold true, which means A implies and implied by B also should hold true. This is one of the things you need to be comfortable with. A question can very well come up regarding whether A is a necessary condition for B or A is a sufficient condition for B, or both necessary as well as sufficient condition for B. So it's better that you try to deal it with this kind of an example to get a comfort level. on the necessary versus sufficient conditions as a part of the execution of the proof. Then the next aspect which we are going to deal with is a few more terms, terminology. In mathematics, whenever we use the word called expression versus equation, the simple difference between these two is here anything you write a combination of something 2x squared plus 3x plus e power 2x, whatever you write, by 1 plus x to the power 3, whatever you write, this is an expression with some plus minus multiplication division power square root, these kind of terms. This is an expression. It's a collection of various terms, various mathematical formulas, various mathematical constants, all put together like this. But if I see some kind of an equal to and something on the right hand side of the equal to, then it becomes an equation. This is the big difference between any mathematical expression versus a mathematical equation. Equation that will definitely contain some form of equal to symbol with something on the left hand side of the equal to and something on the right hand side of the equal to. It need not be a value on both the sides. It could be another expression on the other side. So whenever two expressions are linked with some kind of equality, expression also involves a simple number like 1. That is also an expression. Because any combination of mathematical values or constants or variables with a plus minus division multiplication power kind of scenarios is what we call as an expression. And if both two expressions are linked by an equal to sign, then we call it as a equation. And anything that is joined by a plus sign, we call them as terms. So which means this is one term, this is one term, this is one term. Whereas anything which are joined by a multiplication plus or minus, we call them as terms. Where plus or minus separates them, we call them as terms. Whereas a multiplication or a division separates them, we call them as factors, which means this is one factor, this is another factor. Wherever you find multiplication or division separates, we call them as factors. Otherwise, we call them as terms. Even this is one more thing we have to be comfortable with in this chapter. Then, this chapter also deals with some calculations relating to the exchange rates. So, if I say dollar by rupee is equal to 56, then it means $1 is equal to 56 rupees. So $1 equal to 56 rupees, and sometimes there may be one more thing which says pound to rupee equal to 88. Then I say 1 pound equal to 88 rupees. And the typical question could be, let's say if I am putting up 1000 rupees, or if I am putting up $1,000, how many pounds would it be worth? So now I know $1 equal to 56 rupees. So $1,000 means 56,000 rupees, right? And 1 pound is equal to 88 rupees. So 56,000 pounds, 56,000 rupees will become 56,000 by 88 pounds. So whatever the value that comes out, those many pounds is what will be the calculation. So we need to be very comfortable in terms of doing these calculations. So all we need to be comfortable with is with this kind of an expression, and once we know this expression, we should be able to convert that expression into this format, and after that solving the numericals is a straightforward exercise here. This is one more aspect in this chapter which all of us need to be comfortable with as far as this exam is concerned. Then the next thing that we need to understand in this chapter is something relating to the dates. Generally, we all know that there are some months with 31 days, some months with 30 days, which is a very common thing, whereas February is the only month which will have 28 days in a normal year, whereas it will have 29 days in case of a leap year. So what is this leap year all about? Any year which is divisible by 4. Any year which is divisible by 4, we call it as a leap year. Except if it is a century year, like 1900, 2000, 2100, 1800, 1700, if it is a century year, it has to be divisible by 400 also, not just by 4, but it has to be divisible by 400 also if it is a century year. Divisible by 400 also, then only it's a leap year, which means 2000 is a leap year, whereas 1900 is not, and even the 2100 also will not be a leap year. Whereas 2104, because it's not a century year, or 1996 because it's not a century year, they are all leap years. Whereas 1896 is a leap year, 1904 is a leap year, but 1900 is not a leap year because it's a century year and it is not divisible by 400. So that is what is the definition of a leap year that we need to be comfortable with. And whenever we use the word calendar year, it starts from 1st Jan of that year to 31st December. That is what is a calendar year. And quarters generally are like Jan, Feb and March form a part of the first quarter. Then April, May, June go into second quarter, then third quarter, and then the fourth quarter. That is one more aspect on the definition we have to be comfortable with. And tax years may be different from your normal years. The tax year may be different from your calendar year. In some countries, it may be from 1st April to 31st March, whereas it may be same as calendar year in some countries, or in some countries it's even from 5th April to 6th April to 5th April. So that tax year may be different for different countries, but the calendar year is from 1st Jan to 31st December, and this particular calendar year is called as Gregorian calendar year. All right, and then one more aspect which we are dealing as a part of this chapter is how do we calculate the ages. This is something very important as far as the insurance companies calculations are concerned. Whenever we talk about the ages, there are three definitions of ages we come across: age, last birthday. Lot of insurance company products, policies, they go with the definition of age like this: age nearest birthday. One more definition. And age next birthday. So just try to look at all these three. Age last birthday. Let's say it means, let's say today, okay, my date of birth is 29th August 1978. Very simple way to understand. And today's date is 4th June 2013. Now if you see, what is my exact age? On 29th June, on 29th August 2013, I will complete 35 years. So probably my age today is 34 years and probably 8 9 months, 9 months plus 9 plus months. This is my exact age as of today. If that's the scenario, if I want to find out my age last birthday, then it means only 34. Age next birthday, it is 35. And nearest will be to which of these two it is closest to. Because today I am 34 years, 9 plus months. I am very much closest to my next birthday, not to my last birthday. So this also will show as 35 itself in this example. So what we are typically saying is age last birthday always understates the age, because I will always be elder than what is being represented here, whereas this always overstates my age. I will always be younger than what this is stating, whereas this is averaging. For some people it understates, for some people it's overstates. So that is one more thing we have to be comfortable with as far as our various calculations are concerned, because because most of the insurance applications, let's say whether it is for pricing the premiums or understanding the mortality rates or understanding the number of deaths within a period, for various understanding the number of retirements within a period, for various aspects, actuaries typically depend on the ages. Age calculation is a very important aspect for them, and for different kinds of products they look at the age from different kinds of dimensions. So these three kinds of calculations is something which we have to be very comfortable with. And one last aspect which I would like to touch upon in this chapter is the number of installments. Let's say if someone says I'm paying 10 installments, right? 10 installments half yearly, and the first installment starting today. So after how many years from now my 10th installment will be over? The normal answer that comes out is after 5 years, because I am making two payments in a year and 10 payments have to be made, so after 5 years. But remember, the first payment is being made today, so the second is after 6 months, the third is after 1 year, fourth is 1.5, fifth is 2, sixth is 2.5, seventh is 3, eighth is 3.5, ninth is 4, tenth is only 4.5. So you have to be very careful in addressing problems of this kind, depending on whether you are starting it today or sometime later. The dates and the total time period which is involved in this entire calculations will differ. So you have to make sure that that borderline or boundary line errors don't crop up when you are determining your time intervals, because that will completely break the entire situation of accuracy for various calculations, right? So this is what is the basic content that is covered as a part of the first chapter of ASET. So it all starts off with understanding the various types of numbers, making you comfortable with some types of notations, introducing you to the world of set theory, some mathematical constants, and then differentiating between percentage points and basis points, identifying the world of necessary conditions, sufficient conditions, necessary and sufficient conditions, and a few bit of calculations on exchange rates, and finally moving on to understanding the dates and the concepts of the leap year versus calendar year and the tax year, and the final thing relating to the calculation of the ages: age last birthday, age nearest birthday, and age next birthday. I hope you are comfortable with all these concepts that are covered as a part of the notations chapter of ASET. If you have any further queries regarding this, I suggest you to give me a call on the phone number that is mentioned below: 919848012123. You can also drop in an email to me at any point in time asking for any further clarification on any of the topics discussed above. My email ID being Vamsidhar at pacegurus.com. I request you to visit the website www.pacegurus.com to get a complete update on the various training and consulting programs which we do in the areas of finance and analytics using the tools like Excel, SPSS, VBA, etc. Thanks a lot for listening to this session. Hope you have enjoyed this session. Thank you very much.